So, these things, we're going to talk about them because it might be the last thing you ever see. But probably not in the way you think. So, black holes. We all know what they are. It's everybody's favorite space object to talk about. You know, the Pac-Mans of the universe. Any sci-fi fanboy's worst nightmare because it's going to swallow everything whole and leave nothing left. Well, yes and no. See, black holes are funny because everybody thinks that they might be the key to time travel or something crazy like that. When really and truthfully, all they are just big black balls of death. And that's it. But let me back up because you might be wondering, how did black holes even get here? I'll tell you. Aliens. Joking. Black holes are pretty much just the result of supermassive black stars. They're the result of supermassive stars going supernova, basically kamikazing themselves and then losing to the force of gravity, and all that mass and matter just gets compressed into not a single point, but like a big single point. And it basically goes from looking like this to like this to like this. Don't ask me how that works. I couldn't tell you. So once we get to these big black balls of death, they look a little something like this, and this is kind of how the breakdown of what they look like goes. We've got the singularity, that's like where all the mass is that got compressed into an infinite amount of times. That's what everybody thinks is going to be the key to time travel, because like what happens when you get to the singularity? Nobody knows. I don't think we're ever going to know. I don't think you want to find out. That's just me though. We've got the event horizon. Think of it as the atmosphere, the point of no return, where once you cross this, you're pretty much done. Fun fact, the reason why we call this the event horizon is because, as you've probably guessed, since I said it's the point of no return, looking from the outside, that's the point at which we can't see anything else that happens after you've crossed that point. And that has to do with the fact that because the density of the black hole is so immensely large, the gravitational pull warps space-time to the point where light can't escape the gravitational pull of the black hole. So it either bends around or it just gets absorbed. Black holes eat light. Think about that, which means that the escape velocity is technically infinite. Side note, I don't think it's actually infinite. I just think it's some crazy outlandish number that we just can't calculate with regular math. I don't know if we'll ever be able to calculate it, because in order to calculate it, we'd have to actually be able to go observe it. I don't know about you, but I don't plan on going and observing a black hole anytime soon. I don't think anybody with more than 2 brain cells would want to do that, unless they have the tech to do that. But let's be real here. When are we going to have the tech to do that? So the next 3 parts are kind of the same thing. We've got the photon sphere, the accretion disk, and the relativistic jets. Photon sphere is the light bending around the black hole, like I just explained before. The accretion disk is the black hole eating up all the matter, and it like basically just lighting up, circling around the black hole. It looks like it's spinning, and it is, and I'll get to that in a second. And the relativistic jets that shoot out of both sides are basically just the black hole just shooting light and excess material back out of itself, because it's rapidly consuming stuff as well. It's kind of like a machine, but like a billion times worse, a gazillion times worse. So back to the accretion disk. Remember when I said it looks like it's spinning? And it is. Yeah, black holes spin very fast. Apparently the fastest one clocks in at about 1,000 rotations per second. What does that even look like? Because since a black hole is black, it's fine. The entire thing looks just black. It's spinning, but you can't tell. Now, imagine if it was like blue and yellow or something. What would that even look like? 1,000 times 1 second, blue and yellow. A blue and yellow ball. What? I don't think my brain would be able to process that at all, to the point where trying to would make it probably explode out of my head in the most graphic way possible. I'm sorry, that was really gory, but that was the craziest part of my research, and I'm just like, how? A couple of other things you need to know about black holes is that we can actually calculate how big they are and how big they're going to be based on their Schwarzschild radius. And that's some nice little formula right here that I'm going to pop up somewhere on the screen. Basically, once you put the mass of whatever object it is into this formula, and then you account for the gravitational constant and the mass constant and the speed of light, and because of the way the formula is set up, the size of the black hole is actually significantly smaller than the actual size of the supermassive star, even though the mass is still the same. Just because of the fact that it's so condensed and compact, it does get smaller in size, even though it doesn't lose any mass. Like, to put this in perspective, as large as the sun is, if it were to become a black hole, it would only be about 3 kilometers wide in distance. That's like going from Dwayne The Rock Johnson to like Kevin Hart. It's not as big as you think it'd be. Now, remember when I said the accretion disk is gobbling stuff up, but the jets on both sides are shooting stuff out at the same time? That means the mass stays pretty constant. And because of that fact, the gravitational pull of most black holes doesn't change that much. So, the more massive a black hole is, the more gravitational pull it has, but that gravitational pull doesn't fluctuate or change. So technically that does mean they're not actually the Pac-Mans in the universe, because even though they are, eating mass, they're still shooting it out at the same time. So it's not like they're gaining mass and getting bigger and more powerful to just gobble everything up in the universe until there's nothing left.
Are you sure about that?
And this is actually backed up by the fact that most galaxies the size of the Milky Way, which is our home galaxy, or bigger, have super massive black holes in the center of them, and we're all completely fine. So, we're not actually all doomed. Thank you, NASA. Now, knowing all this and, the fact that black holes essentially eat light, what if I told you that black holes might actually be the last things in the universe to emit light before it goes completely dark? I'm going to switch topics here for a second, so stay with me, because we're going back to the Big Bang.
Huh?
So side note, it was recently brought to my attention that the Big Bang wasn't actually an explosion, according to my professor, but at the time of me recording this, he hasn't explained what it actually was. We'll get to that, he says. So, for the sake of the video and for simplicity's sake, we're just going to say the Big Bang was an explosion. Trivia time. When something explodes, the materials projected from the point of origin do what? A. Briefly accelerate until they reach terminal velocity, abruptly losing all momentum and come to a complete stop. B. A similar answer to A, except the materials begin to decelerate until they lose all forms of kinetic energy. C. Eject inward toward the origin of explosion. Or D. You've never seen it explode. If you chose B, you're correct. If you chose D, I recommend watching Oppenheimer. It's a great movie. Question 2. Is there friction in space? I really hope you got this right. Last question. Establishing that there is no friction in space, if something were to explode in space, the ejected materials would A. Briefly accelerate to terminal velocity and continue to expand at its constant rate. B. Not move at all. C. Create more explosions until nothing remains. Or D. Become a black hole. If you answered A, then you'd be correct. But you're not. How is that possible, you may ask? Well, I'll tell you. According to the know-it-all that goes by the name of Edwin Hubble, he discovered that the universe is actually expanding at an accelerating rate. It's getting faster. So even though you and I and everything else inside the universe abide by the laws of the universe don't apply to the universe itself?
Nah, I'm gonna do my own thing.
And the reason the universe is expanding at an accelerating rate is due to this stuff called dark energy. Side note, dark matter is also a thing. Not the same thing though, so don't say that or somebody's gonna call you stupid. But all you really need to know is that in an incomprehensible amount of time from now, the observable universe will cease to exist. Everything will just be so far apart, you won't be able to see anything. But slightly before that happens, every main sequence star will be dead by then, so the universe will be comprised of nothing more than white dwarfs, red giants waiting to go white dwarf, and black holes. So if by some otherworldly miracle humans actually make it to this part, what you've now entered is the ticking time bomb, which is the inevitable eternal darkness of the universe. First, the red giants will supernova and go white dwarf. Older white dwarfs will lose their heat, thereby losing their light until they fade into the background of space and become black dwarfs. And this will continue to happen with the rest of the white dwarfs until they all fade out and leave nothing but black holes left to remain. Now, remember when I was showing you the different parts of the black hole, like the accretion disk and the jets? That stuff is emitting light. Well, because these black holes still have materials surrounding them, they will continue to produce the last bits of light in the entire universe. Until it's all used up. And then that's it. Darkness. For the rest of time. So if any life forms did exist by that point, the black holes would give them like a few millennia left of light if they really wanted to. But that's only if they find a sustainable way to be at a suitable distance away from the black hole so they don't get swallowed up, but still close enough to make use of the little bit of light that will be given anyway. Which I doubt, because this is so unbelievably far into the future. That's a number I don't even really know how to properly explain. It's a power to a power to a power. Side note, could you imagine just existing in dark space? Like, imagine you're just floating in space, right? Chilling. Then boom, you run into a dead dwarf star that you just couldn't see. What does that even feel like? Because apparently the surface of a dwarf star is like not solid, but it's not liquid either. It's some state of matter that's not possible on Earth. Like, what? Why? Anyway, everything I just explained is the theory of the fate of the universe, and more specifically the end role for black holes. But yeah, black holes actually won't be the end of the universe. The universe will be the end of the universe. I'm done.